Now we are going to define a very famous equivalence relation on group actions called orbit relation. So suppose we have a group G acting on a set A. We're going to say little a and little b are related if A is equal to G dot B for some group element G. Note here that A and B are elements in capital A. So we claim that this is an equivalence relation, which means we need to show it's reflexive. Every element is related to itself. Symmetric, which means that if A is related to B, then B is related to A. And transitive, which means if A is related to B and B is related to C, then A is related to C. So here's the proof. Well, if you multiply any element by the identity element under the group action, you get the element back. So that shows that everything's related to itself. Similarly, suppose A is related to B, then A is equal to G dot B for some G in capital G. Then let's just multiply through by G inverse. Then you see that we get B is equal to G inverse dot A. So B is equivalent to is related to A. So here I'm using this property of the group action. That if I act by G and then by G inverse, it's the same thing as acting by the product. And then the product of an element and its inverse is the identity. Finally, transitivity. If A is related to B and B is related to C, then we have A is equal to G dot B and B is equal to H dot C for some group elements G and H. We'll then take A equals G dot B and substitute. Replace B with H dot C. Then apply this property of the group action. And now we see that A is related to C. So under this equivalence relation, the equivalence classes are called orbits. And so the textbook doesn't use this notation, but it's used in other sources, so we'll use it. We use G of S to denote the orbit of S. Note that it's the set of all G dot S, as G ranges over the entire group. And so one of the other facts that the textbook includes in the proof that the equivalence relation is an equivalence relation is that the size of this orbit is actually the index of the stabilizer subgroup of S in G. So I sometimes see this stated as the orbit stabilizer theorem because it's usually stated in a different way. So it's usually stated as the size of G is the size of an orbit times the size of a stabilizer. And you can see how these two are related. Notice here that one is assuming, obviously, that in the orbit stabilizer theorem, one is assuming that you're working with a finite group in order for this to make sense, although this other fact technically works as long as the equation on the right-hand side is finite. As long as you have finitely many cosets, then it's claiming that your orbit has finite size. So we will prove this, but I will give an application of the orbit stabilizer theorem to state why it's sometimes useful for computing sizes of groups. So let's consider the symmetry group of the cube. Three-dimensional object. So here by symmetries, I'm talking about what are called rigid symmetries. So symmetries that you can actually carry out in physical reality. So this means let's see if I can state this correctly. The correct way to state it is that you've got a linear transformation from R3 to itself. Because remember, the cube is something that's in R3. It's linear and invertible. But more importantly, it's a rigid transformation, which really means that it has no negative eigenvalues in some sense. Which is a theorem we're not going to prove in this course because it's way beyond the scope of this class. But the point is something you can actually get by rotations in space. You can prove that the types of linear transformations you can get by rotations in space, you can't get a negative eigenvalue. I say this because some students in this course might know about Coxeter groups, which is where you actually allow reflections. So I want to avoid reflections for right now, but we can come back to that in a moment. I just want rotational symmetries. And so the symmetries act on the vertex set. There's 8 vertices in a cube. So you ask yourself, given a vertex on a cube, is it possible to move the cube in such a way to move that vertex to any other vertex? The answer should be yes. So the size of the orbit is always 8. All right, so that's half the battle. What is the size of the stabilizer? What are the rigid motions you can make on a cube that puts the cube back where it started but keeps that vertex exactly where it's located? Well, here one actually needs a physical cube to actually see it, but it turns out if you hold the cube up, there's a line connecting this vertex to the opposite vertex, and if you hold the cube up by that line between your 2 fingers, you can rotate these 3 vertices among themselves in a cyclic manner, 120 degrees. So that's 3 possible rotations, and each of those 3 rotations fixes that vertex. And it's hard to prove, but you can show that those are the only 3. And so the size of the group ends up being 24. And yes, you can in fact prove that this group is actually S4. The proof of that relies on pointing out that this group also acts on the diagonals of the cube. So the line segments connecting opposite pairs of vertices, there's 4 of them. And you can prove that every rigid symmetry corresponds to all the possible permutations of those 4. On the other hand, for the people who like Coxeter groups, what happens if you take all symmetries, just not the, including the mirror symmetries? So, and the size of the orbit remains the same. But it turns out you get a lot more elements in the stabilizer. Namely, there's a mirror going through this line segment and then through the opposite edge of the face. So let me draw the top-down view here. And that's a mirror symmetry that fixes that vertex and swaps these 2 vertices with these 2 vertices and preserves the other 4 point-wise. But of course, as you can imagine, that only involves these 4 vertices. You can talk about doing a similar thing with these 2 vertices and their opposite vertices and so on. In other words, taking any one of these edges incident to this vertex and taking the mirror that connects that edge to this opposite edge of the cube. And so there are 3 mirror symmetries. And so you get 48 elements in the group in that case, twice as many. By the way, we see in both these cases that the group action is transitive. which is what we mean when there's only one orbit. Alright then, let's actually try to prove this result. So we need a bijection. Wanted a bijection between the orbit and this set of cosets. Note here we've fixed an S and A. Well, let's try to find a bijection. So let's start over here. So let's take B in the orbit. Then we know B is definitely equal to G dot S for some G. Who wants to do the silly thing? Yeah, let's do the silly thing. The silly thing would to be, well, let's just let sigma of B be the corresponding coset with coset representative G. Why do I say it's silly? Because it's not clear this is well defined. Why? Because remember, this is there exists a G. There might be more than one, right? So we picked a G and defined a map. Well, I mean, what if there was another one? So, I mean, suppose B is also equal to G prime dot S for some G prime. My point is, when you look at lots of examples, there's sometimes more than one group element that sends an element to another one. The easiest one is just looking at a permutation group acting on the set of n elements. The number of permutations that send 1 to 2 is very large. So you can't guarantee that this G was unique, but we can guarantee that the corresponding cosets are the same. So what we want to claim is that G GS is equal to G prime GS. Well, how do we do that? Well, then we just need to show that G inverse G prime is in GS. In other words, that G inverse G prime is a stabilizer of S. Well, how do we do that? Well, just compute G inverse dot G prime dot S. By definition, that's G inverse of G prime S, which is G inverse of B. But at the same time, we could write B as G dot S. And now applying our group action properties, we can move the parentheses over. And now we see that we can cancel. And we get S. So this product is in the stabilizer, and therefore these two cosets are the same. So this function is well defined. Congrats, we got the first step down. We actually do have a well-defined function from the orbit to the set of cosets. Now, of course, we have to consider whether or not this function we just defined is injective. Well, I mean, suppose sigma of B is equal to sigma of C. And what does this tell us? Then what do we have? We have B is G dot S. C was G prime dot S for some G and G prime. Right? These definitions we needed in order to define our function. Sigma of B is GGS, which is simultaneously apparently G prime GS, which is sigma of C. Oh, so we're saying these cosets are the same, which means, of course, that G inverse G prime is actually in the stabilizer. Which, of course, means that G inverse G prime dot S is equal to S. You can obviously guess where we want to go. If we want to show injectivity, we want to claim that B is equal to C. Well, how do we get there? We know that B is equal to G dot S. We now know that you can actually replace S with G inverse times G prime dot S. Now you apply associativity, or I mean the group action property, associativity, and then we cancel out the G times G inverse, and lo and behold, we get G prime S, which is C. So B is equal to C. So the function is in fact injective. So it's well defined and it's injective. The only thing left we need to show is surjectivity. Well, let's just take a coset. And we're going to try B is G dot S. Here I suddenly have to note something that might not have been clear. Notice we defined this function in advance, which means for every single B, we made a choice, G. So and we defined our function in terms of that choice. The reason why I state that is we did that in advance before we hit this part of the proof. So now we're picking an element. It's the case that when we defined our function, we knew that B is of the form G of B dot S. And we defined our function to be G of B, GS. What we can't assume here is that this G sub B and this G are the same a priori. The reason why we can't assume that is because we picked this G a long time ago when we defined this function, and we're only considering this coset now. So the point is, when you're defining a function, you made choices. And so once you've made those choices, you're required to stick to them. So right now I'm assuming we made some choice already in advance. And so what we need to show is that it's actually, that we're okay, that GB of GS is actually the same. That's what we need. So even though we made a choice in advance, it turns out that we actually get what we wanted, that our function is surjective. That's not too hard. What do we need? You just need to show that G inverse times GB is in the stabilizer. I'm sure you can guess, instead of calling it G, yeah, I'll keep calling it G sub B for right now. I didn't do it earlier because it didn't matter until now, but now it's worth emphasizing this point of clarification, because it's worth emphasizing that if I didn't make that point, it would be confusing why I'm spending time on this part of the argument instead of saying that it's clearly true. It's not clearly true. There were choices we made, and we have to stand by them. All right, so this is what we need to show. Oops. We need to show G inverse GB is in G sub S. So how do we show that? Well, it's the same calculation we've already done before, taking advantage of what we know about B. I'll leave it to you to check those details, that you can see that this is equal to G inverse dot B, which is equal to G inverse dot G of B, and of S, and you get the cancellation, exactly like we did with well-definedness. So it's the same proof, but we have to redo it again because we have to emphasize here that it's not immediate, that there is this extra step we have to check.